Hi folks, so welcome to your first online lesson in physics, and the idea of these lessons is that they are narrated PowerPoint slides that I would use in class. So really there's no difference between you watching this video and doing this on class. If you prefer, you can go to my YouTube channel, Slam the Physics, and watch the exact same video if it's easier for you on your phone or on your laptop. Now, the idea of these videos is that you can always pause it at any point, rewind it and watch it again, and basically take notes as we go along. So the topic we're going to do is space, and the reason for this is because a lot of it is more kind of research based and online learning, so it makes it much more easier for you to do this at home. When we get back to class, we will continue on with the course as normal. So let's start by thinking about how big things are. So, for example, how big is a school? How big is Girvan? How big is Scotland? How big is the Earth? And how big is the universe? So, pause the video, write down some numbers. It's just a guess. I'm not looking for a correct answer, and see what you think. Now, hopefully you probably guessed that going down the way, these things get bigger. So the school might be, say, 300-400 metres in length, Girvan a couple of miles, Scotland 500, 400 miles, the Earth maybe thousands of miles, and the universe could be millions and billions and billions and billions and billions of miles. Okay, so the idea of this is really just to get you to think about the size of things relative to each other. And I've got a YouTube link here, which I'm going to post on Teams, that you can watch to show you the size of different planets and objects in space and how they compare. And I really want you to try and notice how Earth compares to all the different things in our solar system and all the different things that we can see in the night sky. And I think you might be pleasantly surprised by where we sit on the scale of size. So what we're going to look at today is cosmological scale. So cosmological just means anything to do with space. It comes from the word cosmology. And in particular, we're going to look at how to define a light year and convert between light year and meters. So a wee bit of calculation at the end of this lesson here. So first of all, distances in astronomy are really large, so it's not practical to use meters or kilometers. Instead, astronomers will use this unit called light years, which you might have heard of already before. And if you've watched that video about the size of different objects in space, you'll appreciate why we really can't use meters or kilometers either. The sizes really do get so big, it really just becomes a number. It's not even easy to try and picture what those size of objects are. Now, one of the key things people get confused about is light year is how far light travels in 1 year. It's a unit of distance and not time, right? So this is a definition that I would like you to try and learn. So if you can copy this into your jotter, please. Okay, definition for a light year. And it's how far light travels in 1 year. People usually think it's a time because of the word year in the actual unit, but it's actually a unit of distance. And so think about when you're in the car and you're asking, are we there yet? Nope, we've still got a couple of 100 miles to go. So how do we calculate how far light travels in 1 year? Well, there's a few things we can do here. First of all, we need to know the speed of light, which is 3 times 10 to the 8 meters per second. And this is actually a really, really important number because Einstein said that nothing can travel faster than this in the universe. So this is the speed limit, if you like, of the universe. And to give you the answer, and we're going to try and work out this answer later on, this is how far light travels in 1 year. It is 9.5 times 10 to the 15 meters. And basically, I'll show you how to get this calculation. You might already figure out how to do it if you remember our calculations with speed, distance, time. Now, I don't expect you to remember this number, but it is handy to know how to get to this number. And to give you an idea of the size of this number, that's light travelling around the Earth 236 million times in a year. So you can imagine how many times a beam of light would go around the year travelling at that speed. So how do we convert light year to meters? Well, first of all, we're going to use our good old friend speed, distance, time. And very nicely, the units are already in the correct form. Speed is in meters per second, distance is in meters, and time is in seconds. So remember, we've just been doing calculations on these, and remember how to use the triangle. Whatever quantity we want, we cover it up, and whatever's left is our equation. So if we cover up speed, we get distance over time. If we want distance, then we cover up distance, then we get speed times time. If we want time, we cover up time, then we get distance over speed. So you'll be using these in the worksheets that I've uploaded as your assignments. So how do we convert light years to meters? So I would like to copy these steps down bit by bit. If I'm going too quickly, feel free to pause the video and replay the section again. Otherwise, you can just look at it at the end. So first of all, we take the speed of light as 3 times 10 to the 8 meters per second. Now, the key thing here is that remember a light year is how far light travels in 1 year. So the time it travels is 1 year. And remember the unit for time is in seconds. So we need to convert 1 year into seconds. So first of all, we do it step by step. In 1 year, there are 365 days. So we multiply 1 by 365. That's changed it to days, so we now need to change days into hours. How many hours are there in a day? Hopefully you can tell me it's 24. So the next step we do is 1 times 365 times 24 hours. So that's how many hours there are in a year. Feel free to put this in your calculator if you wish. And then we change this to minutes. How many minutes are there in an hour? Again, hopefully you can tell me it's 60. So we multiply by 60 at the end. Again, you can put that in your calculator. And we're almost there. How many minutes are there, seconds, sorry, are there in a minute? And again, hopefully you can tell me it is 60. So that gives us an answer of 31,536,000 seconds. So you can see we're starting to deal with some really, really large numbers here. So that's kind of the tricky bit, because now we can use our equation to calculate the distance travelled by light. Excuse me. So we start with our equation. So remember, speed is equal to distance over time. And remember the technique I showed you, or the routine I showed you, plug in your numbers first before you rearrange it. So we plug in the speed of light, so it's 3 times 10 to the 8. And you'll have to bear with me because I'm writing this on my mouse pad, which is not the easiest thing to write with. And that's equal to distance over the time that we've just calculated. So it's 31,536,000 seconds. Okay, and we're almost there, because to get the distance, remember you can use your triangle, but I hope you're pretty good at this now. Oops. You can rearrange this for distance, which is equal to 3 times 10 to the 8 times, oops, get it properly done, 31,536,000 seconds. And if you enter that into your calculator, hopefully you will get the same answer as we did before, around 9.5 times 10 to the 15 if you round it up. So that's the calculation that I want you to be able to do. You've done a similar calculation before. You might not have changed 1 year into seconds, but you've seen the process. It's the same every time. Okay, so now that we know how to calculate or convert light years into meters, let's give you an idea of the size of this measurement. So one of the nearest suns to Earth is a sun called Proxima Centauri. And according to astronomers, this star is another word for suns, is about 4.3 light years away from Earth. So what that means is that light has to travel 4.3 years to get there. So if we were on a spaceship traveling at the speed of light, it would take us 4.3 years to get to that sun. If we wanted to do a return journey, it would take us 8.6 years to go there and back. And that's if we were able to travel at the speed of light. And remember, Einstein said nothing can travel faster than that. So that poses a lot of questions about how do we travel among planets and different suns. It means that space travel can be very, very long, and that has other issues as well, which we'll try and explore later on in this course. And just to give you a wee idea, this is where our sun is meant to be in this photograph, and this is sort of the distance in the sky between the sun and the Proxima Centauri star. And this is obviously not to scale, but it just gives you a rough idea of it. Now this photograph here is of the Milky Way, and this is part of our own galaxy that the Earth is in, and it's a real photograph. It's not CGI'd, it's not fake. Again, I'll explain to you why it is that you can see this in some parts of the skies but not in other parts of the skies later on. And to give you an idea of how big our Milky Way is, it is 100,000 light years across. So what that means is, if light was to travel from one edge of the galaxy to the other, it would take 100,000 years. So you can imagine how big that distance is and how many planets there must be in our own galaxy. And this is why astronomers and scientists will quite often say they're pretty convinced there is life out there because the universe, the galaxy that we're in, is so big. At the same time, you could argue because it's so big, it makes it really, really difficult to communicate with different aliens if they did exist there. And again, we'll look at these in a bit more detail as we get into this course. To give you a wee bit more information about our own galaxy, this is an artist's impression of what our galaxy looks like, so it's not a real photograph. And you can see we reckon our galaxy has this lovely kind of spiral shape, and in fact it's called a spiral galaxy. You do get other types of galaxies which we'll look at again later on, but this is what our own galaxy would look like. And as I said to you, it would take 100,000 years for light to travel from one end of our galaxy to the other end of our galaxy. Now, let's get on to doing some calculations with this so you can see how astronomers might use this unit of measurement. So again, I would like to write this down because this is a worked example which you can then look through when you're doing your calculations. If you get stuck or if you're not sure how to do the calculations, I would recommend you look through this, or you can play the video for this section again. So you will need your scientific calculator. You will obviously need your jotter and a pen or a pencil. So I'd like to start by copying down what's on the screen there. So a black hole is 2.85 times 10 to 16 meters from our sun. Calculate how far away it is in light years. Now I should point out this is not a real life example, because if a black hole was that close, we probably wouldn't be able to exist the way we do. So the trick to doing these questions, as always in my courses, is to use our KFC routine. And remember, that means know it, find it, calculate it. So I've already given you the length of a light year to start off with, so that way we've got that written down already. The other bit of information we have is that the distance is 2.85 times 10 to the 16 meters. Okay. And we're asked to calculate how far away it is from us in light years. So really, there's no equation for this one because it's just converting from one type to another. So for example, how would you convert meters into kilometers? Hopefully you can tell me it's divide by 1,000. So in this case here, we want to convert from meters into light years. So what we do is we take our 2.85 times 10 to 16 and we divide it by the length of one light year. So it's really a wee bit of basic arithmetic. There's really nothing tricky about this. There's no equations to rearrange. There's nothing to really think about. As long as you have everything in the same units and you get the division rather than multiplication, you will be okay. And then try this in your calculator and hopefully you should find you get an answer of 3. And remember the units we're converting to light years, so it's LY. So in light years, this black hole is 3 light years away from us. So that is another way for astronomers to write that distance, and you can see it's much more easier than writing out this big number over here. So to summarize, to convert from meters into light years, we divide by 9.5 times 10 to the 15. So you might want to write that down. I haven't typed it up in here, but you can write this down. To convert from meters into light years, divide by 9.5 times 10 to the 15. Okay, in fact, I'll try and write it down. So meters to light years, you divide by 9.5 times 10 to the 15. And remember, your answer will always be in light years. Okay, pretty straightforward. Let's look at the next one now. So, second example, the Voyager probe, and this is an actual probe that scientists have sent out, and in fact, it's the object that has travelled the furthest that we've ever released into space. And again, we can look at this a bit later on. So lots of really exciting and interesting things to look ahead to in this topic here. Anyhow, back to the question. The only satellite to leave the solar system has travelled 4.5 light years. Now again, I've made this example up, so don't take this as fact. Calculate how far this is in units of meters. Now, again, we can use the same technique as well, write down what we've got and then do the conversion. But let's step back a little bit and see what it's asking us to do. Here, it's given us the units in light years, and we want to convert to meters now. So if we think about it, it's doing the opposite of what we did earlier. So in the first example, we divided to go from meters into light years. What do you think we have to do if we want to go the opposite way around from light years into meters? Okay, pause the video and have a wee think. Hopefully you were able to tell me that if we're doing the opposite to the first example, we are going to multiply, right? And that is actually how we do it. But let's just do the working. So again, I'd like to copy this example down and copy the working down as well. So I'm going to plug ahead here and just write this down because you can obviously pause the video at any point and do the copying. So that's 4.5 light years. And what we want to do is 4.5 times 9.5 times 10 to the 15 meters. And if you do that on your calculator, you should get an answer of 42, I'll write it down here for you, 42.75 times 10 to the 15 meters. And I'm quite happy for you to leave it as that. You don't need to simplify it anymore or tidy it up. You can leave it like that. And that is our answer there. Okay, so nice and straightforward again. There's nothing tricky there in terms of rearranging equations, etc. It's simply remembering to go from light years to meters. You multiply by 9.5 times 10 to the 15. Okay, and in fact, I wouldn't even remember this one. I would just remember the first example because you know if it's the opposite case, you can always work it out. Now you've covered enough material there to do the calculations for the first part of the worksheet. You can go and try those if you want, or you can keep going on. If I remember that correctly, if you find the worksheet doesn't make sense, come back to this because we might not have covered enough. I might have remembered that wrong. But we've got one final example to look at, so you might want to check this final example first. So Proxima Centauri is 4.3 light years from Earth. An astronaut travels at 25,000 meters per second to get there. Calculate the distance from Proxima Centauri to Earth and calculate how long it would take the astronaut to reach Proxima Centauri from Earth, assuming he's traveling at the speed here. So again, I'd like to copy this example into your notes and let's work through this. So I've made a wee smaller version so I can fit things in. Now, if you want, try this yourself. In fact, I would like to see if you can do this yourself. You should certainly be able to do the first part yourself. The second bit, I'm going to give you a wee clue. You're going to have to use the equation speed is equal to distance over time. So pause the video, try it yourself, and then I'm going to take you through it. Okay, so here's the solution on how to do it. So first of all, we are converting a distance from light years into meters. So remember, light years into meters, we have to multiply by not 4.3, we have to multiply by 9.5 times 10 to the 15. Okay, so this is our conversion into meters. So if you do this, you can work it out. Okay, and that will give you an answer in meters. Made a meters there. Okay, nice and straightforward. I've not got the answer here, but I'm assuming you can do this on your calculator. The second point now is, and my clue to you was to use speed distance over time. So let's write our equation down as we always do. Now, in this case, we're talking about the astronaut. So we're going to use the astronaut speed, which is 25,000 meters. So remember, the next step of our calculations is we always plug in our numbers first. So 25,000 is equal to a distance of our answer here. Now, I'm just going to call this x because I've not worked it out, but just so you know that we've subbed in for our number from answer part 1. And we want to work out the time. And so we then rearrange it for time. Time, remember, is equal to the distance travelled, x, divided by the speed, 25,000. Okay, so if you work that out on your calculator, you can tell me or post to me the answer on our teams and surprise me. Hopefully you all get the same answer, folks, right? And you'll probably see that this number is really, really huge. If you want to give you a wee bit more context, an idea of how big this number is, you can convert it into hours or even days. So to do that, you would divide by 60 to change it to minutes, divide your answer by 60 again to change it into hours, divide it by 24 to change it into days, and that will give you an idea of how long the astronaut will have to travel. Now, just to wrap up the lesson, there's just a wee bit more info I want to give you and some facts to kind of put this into some context. But we know the sun, the light from the sun, takes 8 minutes to reach us. That's how long the distance is between the sun and the earth. So this means we are looking at the past from 8 minutes ago, which is a really weird idea. If you look out the window just now and you're looking at the sunlight, that sunlight is actually 8 minutes from the past. And the further light travels to reach us, the further back in time we're looking at. So, for example, if, say, the sun was to explode suddenly, we wouldn't know about it until 8 minutes after it's happened, because that's how long it takes for the light to reach us. So if we wanted to do something to save the sun, and we were watching it to tell us when to do something, it would actually be too late, because by the time we see it, the sun's already exploded, because it's taken 8 minutes for that information to reach us. It also means if you look at the night sky, you actually see further at night time than you do at daytime, because at night time you can see the light from stars, and as you know, they have traveled several hundreds of light years to get to us. So in fact, when you look at the night sky, you are seeing something from the past. So it's a really weird idea that because the light takes so long to reach us, what we're seeing is not the present. It's actually something that has happened several months, several years, or even several hundreds of years ago. Okay, and with that thought, I'll leave you there to try the calculations. As always, if you've got any issues, email me on my Glow account or you can contact me on Teams.